So the next thing we're going to be talking about is aromatic compounds. And one thing to note for the MCAT is that this is a very small topic. They're kind of phasing out aromatic compounds for the MCAT. So just know very, very basic stuff about it and you should be fine. You don't need to go as in depth as I know you guys did in your university level Ochem classes. Alright, so aromatics, if we remember, looks something like this. So this is the most common one, and that's just called benzene. And so there's basic rules. There's 3 rules. There's 4, but I kind of combine them into 3 of how we can assign whether or not something's aromatic or not. And remember, you knew something about aromatic, non-aromatic, and anti-aromatic. Don't worry about that for the MCAT. It's just, is it aromatic or not? We don't need to know the distinguishing fact between non-aromatic and anti-aromatic. That's not important. We just need to know, is it aromatic? Alright? So 3 rules go like this. So for it to be aromatic, it has to follow all 3 of these rules. So all the carbons are sp2, meaning that they all are planar. Alright, so that usually is split up into 2 different rules, but they're pretty much the same thing. So sp2 means it's trigonal planar, means it has 3 groups coming out of it. Alright, so it's always going to be planar. Alright, second rule is that it's cyclic, so it has to all attach together. So it has to be all cyclic. For example, like that would be cyclic, that would be cyclic, this would not be cyclic. Alright. Then the final one is probably most important, and the one we forget most is Huckel's rule. So the Huckel's rule says 4n plus 2 is the number of pi electrons. Alright, so what does that mean? So say we have 10 pi electrons. Alright, would that follow Huckel's rule? And the answer is yes. If n equals 2, 4n plus 2 equals 10. Alright, so it just means n has to be an integer. If it follows that, then it's okay. If there's 8 pi electrons, would that be aromatic? And the answer is no. If it has 8 pi electrons, alright, then n would have to be 6 over 4. Alright, so that's not an integer, so n has to be an integer. So an example of that would be, for example, something with 8 carbons. Alright, we see this molecule right here. Alright, 8 carbons, alright, and it has 8 pi electrons, right? We would see 2 in each of these double bonds, so that would be 8 total electrons. So if it's 8, then that would mean it is not aromatic. So this is not aromatic, so it's not aromatic. But in this case, it has 6 pi electrons. 4 times 1 plus 2 equals 6. So this would be aromatic, that benzene ring. Alright, so here are some examples. Some of them may break it, some of them may be right. Alright, so for example, this one right here, is it aromatic or not? And the answer is no. And we see right here, it breaks the first rule. Right? It is not planar. Not all the carbons are sp2. The majority of them are, but one of them is not, and that's why it doesn't follow. For the second one, most people would probably say, oh, it's not. But the answer is it actually is. And there's a reason why. Alright? So what happens is these lone electrons get pushed down, and we get this resonance structure. Sorry, this is not there. Alright, so what happens in that case is that instead of just having 4 pi electrons that are now resonating in between, we have 6 pi electrons that are resonating within. Alright, that was the only rule that this one kind of looked like it didn't fit, is the third rule of Huckel's rule. Alright, the fact that when we push down and resonate these lone pairs, now we can say that those are one of the pi electrons that we can use. Okay, so these would be considered pi electrons because they can resonate in. If they can resonate in, then we consider them part of the pi electrons, and we would use that as the 4n plus 2. Alright, so we always have to watch out for these lone pairs. If they can resonate in, then we would count those as 2 pi electrons, and that's why we have 6 total pi electrons. 4n plus 2 equals 6, we would get n equals 1 as an integer, and so that checks out. And obviously it's cyclic, and all carbons are sp2 as well, right? So everything's good. So the next thing we're going to be looking at is just some simple reactions. We don't need to know that many, but this is probably one of the more important ones, and a lot of them we can kind of just guess, and we would get to the right answer. So the first one is when we add Br2 and FeBr3. I think you guys all can guess what this would be. and it will just add on to a BR. And I'm going to draw it here because you guys might not be able to see up there. So it'll just add a BR anywhere because they're all, it's symmetrical, so it doesn't matter where. But here's kind of the case when we kind of have to get the naming down. So the first one is it just has a methyl at the top. We can call this toluene. That's more of a common name that is more known for the MCAT. So what I've drawn here are everything is bromotoluene. Okay, so all three of these are bromotoluene. Do you guys agree? Everything has a bromo on it, and it has the main group of toluene right there. But just like when we named it before, they're not all the same. Remember when we named it, we had to go 1, 2, 3, 4, 5, 6, that type of thing. Well, in this case with benzene rings, we're going to give something with an ortho, meta, and para. Okay? And so just luckily for us, I've drawn it in that same order. Ortho, meta, and para. Okay? So ortho is right next to the main group that we're looking at, and in meta it's the second, and then the para it's the third. So finally, this is a lot to kind of take in, but this is probably the hardest part that you guys remember from Ochem is this ortho, para directing, or meta directing, and these are also known as activators and deactivators. Okay, so when we're looking at these groups, right, we have a OR here, and in this case we have an NO2. How do we know whether or not we're going to get an ortho, para, or a meta? And so let's just see what those look like. So in the ortho para, we're going to get a BR in the ortho position and also in the para position. Okay? And so, just know those go together, and that's fine. Ortho and para will always react together. Okay? And meta is the one that's all by itself, and so our compound will look something like this. And so that's fine. That's fine that we know that's what ortho-para directing reactions will look like, and that's what meta-directing. But the problem is they're not going to say that this OR is a ortho-para director or this NO2 is a meta-director. So right here we have all the examples of what an ortho-para director may be, and on this side we have all the meta-directors. But the problem is it's way too much to memorize. You can't memorize that, so we have a little bit of a generalization. And obviously these generalizations always have some exceptions to them, so you kind of have to, while you do examples, you kind of figure those out on your own. But a basic generalization we can say is if it's electron donating, it's going to be an activator, and it's going to be ortho-para directing. Okay? So if it can donate electrons, then it's an ortho-para directing. If it's electron withdrawing, and I'm always talking about these groups right here, so like NO2 would be electron withdrawing. It's going to be also known as the deactivator, and it's going to be a meta-director. Okay? And one thing to keep in mind is very, very important is that the acidity, remember I said before when we dealt with acidity that knowing if something is more acidic or less acidic is going to be very important for the MCAT. If it's ortho-para directing, it's going to decrease acidity. Meta-directing is going to increase acidity. So now you may be asking, what did I even mean by electron donating and electron withdrawing? So an easy way to just remember that is if it has electrons that can donate into the benzene ring, it's going to be electron donating. So we'll see what that looks like. So we know that there's going to be two lone pairs of electrons on that O right there. If we push them down like that, we can get a resonance structure that looks something like this. Okay? And these electrons this would be a lone pair of electrons, and they can go resonate throughout the entire ring. So because electrons were donated from that OR group, then we would call this electron donating. And remember we saw NO2 before, and you may think, well, NO2 probably can donate electrons as well. The problem is NO2 looks something like that. Okay, so it's kind of tricky. You guys may not have guessed that it looks like that, but NO2 looks like this. So there actually is no lone pairs. Everything is fine and it checks out. We have a complete octet and a positive charge in the end. And so that's why we won't see anything that can actually donate electrons, because there is no lone pair of electrons on the end. Because that is the case, it's electron withdrawing. Okay? So if it can donate electrons, if it has a lone pair of electrons, electron donating. If it can't, electron withdrawing. Okay? So as long as you have that checked out, make those generalizations. Always make your life a little bit easier for the MCAT.
If you like our videos, be sure to check out our website, mcatforme.com. The videos accompany our free MCAT course syllabus for a 3-month study plan. We have the books you should use, the homeworks to do, videos to watch, and chapters to read. Also, be sure to subscribe to our channel. We'll have new videos every Tuesday, Thursday, and Sunday. Thank you.